In Lecture 6, we're going to want to talk about some more issues related to model fitting, evaluation, and tuning of models. And this is going to be one of the last lectures. We'll talk a little bit more about this next time, but then we're going to get into classification pretty quickly. So I wanted to start off by talking about the goal of model evaluation. And the goal of model evaluation is to determine how well a model building process or procedure is going to work for data. So our goal is to determine how well a model building procedure will work. That is, how accurate is it going to be? And this sounds trivial, but this is a pretty actually a deep statement here. This is a really important statement because people lose sight of this when they're doing model evaluation a lot. So the idea is, what we have in mind is that I have some data that follows some probability distribution. Data follows some probability distribution. So my data were maybe, how do I want to do this? Maybe my data were script D. D is in some probability distribution. You could write it that way if you want. So this would be my data, and this would be the probability, right? And we don't know exactly what that is, and there are different ways of thinking about what that might be, whether it be linear or nonlinear, how all the variables are related. But generally, we imagine there's some data generating process that probabilistically generates data according to some process or some distribution, and that's data we have. And the goal, again, of model evaluation is to determine how well a particular model building procedure will work for our data. So we're assuming that we have some kind of domain of data. We have images streaming in from a self-driving car, right? So images streaming in. And that domain of data looks like something. It has some probabilistic distribution of things that we're seeing. Something simpler would be, we observe. What's a simpler example? I observe water quality samples in a river, right? And they're tell us something about the quality of the water in the river, but they have some probabilistic process behind them. We want to build a model, an algorithm, a machine learning, a statistical learning approach for predicting things. And we want to evaluate, be able to go to our boss and say how well this is going to work. Or when we're trying to publish it, we need to tell our peers, how well is this going to work? And so obviously we want to evaluate, and we want to estimate how well it will work. So the goal of model building process is basically to form an estimate of how well the procedure, a model created by a certain procedure will work on unforeseen data. And again, this seems very trivial, but it's a little deeper, because what we're evaluating is the procedure by which we build the model. Ultimately what we care about is, if I fit a regression to this using these variables, how well is that going to work on future data? If I fit a KNN model and I tune, I play around with different values of K, and I send it out into the real world, how well is it going to predict? So there are all different kinds of procedures by which we could take existing algorithms, combine them in various ways. And it's easy to get this wrong with what model evaluation really means and what the point of it is. The point is to say, I've come up with a procedure to build a model that will predict in this domain of data. How well is that going to do when I send it out into the real world? So we have ways of evaluating. We have all these different metrics, and it really doesn't matter exactly which one you use. I mean, this is a separate discussion. But we have these metrics, RSS, RMSE, MSE, R-squared, all of these different things, which I kind of very quickly went through because they're all kind of very similar in this kind of intro stats level knowledge. But what we do with those is important so that we get it right. So obviously, so let's talk about the first thing we can do, which is, let's say, we're going to call this, what do we want to call this? Train data set versus validation data set versus testing data set. And people get this wrong all the time in this terminology, and I've probably said it wrong many times, but we'll get it right here. So here's the first thing that people do. Now I'm going to talk about the pitfalls of what could happen if you're not careful with how you do this process. So we all know that we have some data, and if you just take your data and you build a model and then you evaluate on that data, right, the model is going to be overly optimistic. You can't evaluate on your training data. The model is going to be overly optimistic because you just evaluate on the data that you've used. It's like giving the answers to students and then ask them to take a test. They're going to do better than they should. They're going to do better than they would on an exam where they don't have the answers. That's exactly what the learning problem is. If you give the algorithm the answers, it's going to figure out how to do better. And then if you put it on, you apply it to some data where it doesn't know the answers, if you're expecting it to do as well as in the case where it did know the answers, you're going to be surprised, right? So what do we do in that case, right? We hold out some data, and I'm going to call this the validation data. Often people will call this testing data. We're going to talk about the difference between testing and validation. It doesn't really matter what the terminology is, but we'll talk about it. So we take our data, we split it into a validation set, and we split it into a training data set, right? And what do? We take the training data set and we build a model. And so here is this arrow is our model building procedure. All right. There's some procedure. Maybe it's linear regression. Maybe it's KNN regression. But it takes the training data and it spits out a model, an F hat. And what we do is, because we can't evaluate this model on the training data, that would be circular. What we do is we take this holdout set, this validation set, and we combine it with the model, and we make the model predict on this data it's never seen before. And because it's never seen before, you're not going to run into the problem of overfitting or being too optimistic. And you get your evaluation metric, RSS, RMSE, whatever it is. So that's all well and fine. That's a very reasonable thing to do. And this is something that people do all the time in practice. Here's where it starts to get a bit dangerous. So I do this procedure, I build the model, I get my evaluation metric, but I'm not happy with my evaluation. It doesn't do as well as I would hope. So what do? Well, I go back and I tweak my model, right? I tweak my model, retrain it. So as I change my model building procedure, I retrain it. Maybe I change the covariates, maybe I change a hyperparameter like K, and I retrain it. I get a new model, and I take that model and I evaluate it on my validation set. and I get my evaluation metric, and maybe it's better, and I say, aha, this is a better model. I report that number to my boss, right? That is inherently dangerous because what we have just done is we have brought the validation data, which is supposed to be data the model never saw. The whole model building procedure does not see that. It is not upstream of it. The only thing the model building procedure is it sees the training data and it's supposed to spit out the model. But now what you've done is you didn't like your original model, and so you went back and you got the validation data. You didn't like the original model because of what you saw in the validation data. And that validation data, now if you go change your model, is informing a new procedure that produces a new model. And so now kind of through the back door here, the model or the model building procedure has actually started to get some sense of what the validation data is, because in this case, what I've done is I've kind of used my opinion about what how good the validation data is to inform how I rebuild the model, and then I evaluate. Eventually, my evaluation metric uses the validation. So basically, I've just inserted my validation data kind of into the new procedure. So this is related to what's called like p-hacking, or like, or statisticians will also often call it going on a fishing trip. You're going to find some fish. You go on a fishing trip, you're going to find fish, right? So the idea is you're looking for something. You're going to find something. It's kind of related to that. But in this case, basically you're now taking the holdout set, just not your model procedure is not supposed to know anything about, and you've kind of inserted in it. Now this, you may say, well, let's just not do that. But people do this all the time. The greater sin is maybe I want to optimize over what we might call a hyperparameter. These are often called tuning parameters. Tuning parameter. So this is something like k and k and n. It's a parameter that I'm free to choose, or the number of covariates, or the exact covariates in a regression. I'm free to choose what covariates I include. I'm free to choose what value of k I choose. So oftentimes what people will do is maybe they'll explicitly, and we did this last time in the lab, and we talked about this in the lecture, and so we need to talk about, that was a little bit, well, we'll talk about, it was a reasonable thing to do, but you have to be careful about over-interpreting the results, because that is the more formal way of doing this. So if I add in this arrow where I say, what I'm actually going to do is I'm going to build my model, evaluate it, and then I'm going to do it again. I'm going to circle back and change my value k and fit it for another value k and change it for another value k and loop over and search over a whole bunch of values of k, and maybe I choose the value, I fit it with the value of k that has the smallest metric, smallest RSS, right? It's a reasonable thing to do. It's a fine procedure. But you have to be careful to understand that your evaluation metric in this case, if I loop back and just fit and fit and fit until choose the model that minimizes my, say, training metric, minimizes the metric I calculate for my validation set, is I'm basically including this validation data in this loop. So now my model building procedure includes the validation data, right? So maybe I should put this arrow up here. What we're doing is we're inserting it into the procedure, right? Where I'm going to loop over values of k, fit for a bunch of different values of k. So it is not true now that the ultimate model kind of didn't have any information about the validation data set, because the value of, for instance, if we optimize over the different values of k, the value of k that was chosen minimizes this evaluation metric, which was calculated from the validation data. Doing that loop is fine, but you then have to understand that this evaluation metric will be overly optimistic with the same problem with the training data, right? So, that fit regression, I minimize you can view fitting regression as minimizing the training RSS. A very reasonable thing to do. It's just you can't overinterpret that training RSS because it will be overly optimistic about how low it is. In the same way, it's fine to optimize over a hyperparameter like k, but if I do that, my resulting model, or my resulting metric, if I say I loop over all my values of k and I choose the model with the value of k with the lowest training error, or lowest, validation error from my validation set, great way to build your model, but that metric is going to be overly optimistic because I've just optimized over it. I've chosen the one with the smallest, and it may not be representative. The validation set is not truly an independent set now because it's kind of in the loop now. Another way of viewing this is that I could basically draw a box, right? So here my model building procedure only has the training data coming into it, the original one, before I add this loop. And so the validation data set didn't make it in there. I could build a new model building procedure. I could just put this all in a box, and this is my new model building procedure, right? So my model building procedure is I loop over all the values. I'm going to fit a k and n model. I'm going to loop over all the values of k, and I'm going to choose the one with the smallest valuation metric, the smallest validation metric. So that could be called my procedure, because out of it, eventually, what you produce is you produce some final model, right? My final model is maybe I loop over my values of k and I choose the one with the smallest validation error, and that's my final model, right? But if you look now, if I just you can just view that whole loop of optimizing over the hyperparameter k as a model building procedure itself. And what's feeding this procedure? The training data and the validation data. And the output is whatever final model, maybe the one that you use at the value of k with the minimum training or validation metric. What's informing this final model is both the validation and the training data. And so if I evaluate this final model on that validation data, it's overly optimistic. In the same way as if I evaluated the simpler model on the training data, it's overly optimistic. And that procedure of kind of looping over the values of k includes the validation data, and it's overly optimistic if I just evaluate my final model on that. Okay, so this is a point that people get wrong quite a bit, and you have to be really careful. So one way of solving this problem is to have not only a training data set, a validation data set, but also have what we call a test data set. And the test data set, if I want to say optimize over a hyperparameter like k, I split my data into test, training, validation, and test. I build a model with my training. I evaluate it on my validation data set, and I do that over a bunch of different models. Maybe I'm optimizing over a hyperparameter. Maybe I'm choosing different covariates to go in my model. And then I choose the model with the lowest validation error. That's my final model. And then I have this test data set that's never been touched before by that whole loopy procedure there. And this is I can use to calculate my final metric, my final evaluation metric. And notice that this test data set was never involved in the optimization procedure, say for optimizing hyperparameter or choosing any of that. So that is that's what people will do. People are really serious about this. When they write a paper, they will split their data at the beginning, lock it away in a room, do whatever machinations they want to build their model, and then before they publish, they run it once on their test data set, and that's what it is. So they've never been influenced by that test data set ever. So at the beginning, I made this big stink about how the goal of a model evaluation is to determine how well a model building procedure will work on our data. So this is what I mean, right? My model building procedure may be I split into test, training, and validation. and I optimize over the parameter k to choose the one with the smallest validation error, and that's my model, right? And then the point of holding out this test set is to give me a estimate. This final metric is an estimate at the end of the day of how well does this model perform on new data, right? What it is approximating is that I drew, basically two data sets from my probability distribution P, right? I drew one, I used to build the model, and I drew another, and I used it to evaluate the model, right? Or in our case, we have, say, 3: training, validation, and test. But at the end of the day, the point of, say, splitting into training, validation, and test is to get an estimate. So this thing is an estimate of how this procedure, and the procedure can be whatever you want. Maybe it's testing some linear regression models against some KNN models against some fancier whatever neural network models. It can be whatever you want, but you come up with a procedure. And the point of calculating the metrics is to estimate how this procedure, get an estimate of how, of how a model produced by this procedure will perform on new data. All right, that's all you're just trying to get an estimate so you can tell your boss, if we build the model this way, it's going to be 95% effective. If we build the model this way, it's going to have an RSS about this on similar data, right? So that's the idea, is you're trying to say, if we evaluate on hopefully similar data in the real world, this is what we can expect as performance. So if I have, this is, how percentage of the time I expect to, do things wrong, and this is how, eventually they'll take it, in a business, they'd say, and this is how much money we expect to lose, or this is, or expect to gain, or what our probability of profit or not is, right? But it's just an estimate of what the procedure is. Be that procedure, building a regression model, or building a KNN model and looping over and optimizing over the value of K, right? I make a big deal of that because at the end of the day, you're going to build the model. Like if I have a data set, you're going to build the model using all of the data you have. Right? So at the end of the day, right, you're not going to hold out data as a test set. If you actually want to put this model into production, actually use it in the real world, you're going to throw all the data you can at it, right? And that's totally fine. If you throw all the data you own at it, you won't be able to estimate how well it performs. And so what you could do is you would what happens in production is they do this thing and have training data set, validation data set. They use the validation and the training builds it, the validation helps you optimize over parameters, and then they use a test set to estimate how well, if we build the model this way, using regression with these covariates, what's the accuracy of the resulting model likely to be? Cool. But at the end of the day, when you say, okay, so let's go build that model. So they go build the model, and you're going to use everything you have, right? You're not going to necessarily hold out training data, right? And the only point of calculating the metrics, the evaluation metrics, is to get an estimate of how well that the model that you ultimately build is going to perform. Because if you use all the data you have, you can't estimate it. So you have to play these games with holding out data to estimate. Okay. Let's talk briefly about cross-validation. So what I'll just say about cross-validation, in fact, let's write it quicker. Cross-validation is that this has the same problems. Cross-validation is just a fancier way of estimating the generalizable performance. Let's say a fancier way of estimating performance. Cross-validation is basically you're taking multiple samples instead of one sample. And so you can get a better estimate by reducing the variance of any particular estimate, right? If you just have one training data set, one validation data set, one test data set, you have those, you have a kind of n of 1, you get what you want, but cross-validation basis says, well, we can just basically take multiple samples and then we'll kind of average them together and we'll get a lower variance for our estimate, and so it will be a better estimate, right? So what cross-validation does, as we said last time, is it takes my data and it splits it into a bunch of folds. Fold 1, fold 2, ... all the way up to fold, let's say V for validation. Let's just use a different parameter than K, right? So you can call it V fold cross-validation. And the procedure here is that what we do is we basically loop for little v 1 to capital V. We fit on, we're basically doing a train test split a bunch of times, right? So you fit on all but fold K, and then you evaluate on fold K, and maybe I can call that MK for metric, for the kth metric. So you do this a bunch of times, and then M, my final metric, say final metric is equal to maybe, I don't know, the mean, the median, whatever, of the MKs, right? Of all the metrics I calculate. So basically you're just sampling a bunch of times. That's going to bug me. That should be a circle, right? So, okay. But cross-validation doesn't solve any of the issues we talked about. It's just a fancier way of getting an evaluation metric. And so you could run it at the same time, same kinds of problems. So let's say to avoid, to optimize over, say, typically people think of this as optimizing over hyperparameter, basically just trying out different models. You can use what's called nested cross-validation. And in the same way that we went from a training and a validation set to a training, validation, and test, nested is just going to basically nest cross-validation, so you're always holding out something that's like the test set. And because, if you were to do this, the same thing would happen if I were to cross-validate for one value of, say I tried a bunch of different values of K for a K and N model, but for each value I estimated its performance using cross-validation. That doesn't solve the problem that if I choose the value of K that minimizes whatever now the cross-validated metric is, just a fancier metric, you're still going to have all the same problems. So before I say the evaluation metric, just say cross-validated evaluation metric, right? Still have all the same problems, where it's going to be overly optimistic for the final model that you choose. Nested cross-validation is basically a way of solving this, where basically what we do is we again, let me just write out the procedure. For nested cross-validation, again, so we have our, let's say, V folds. Across all these folds, what we do is we are gonna, let me just write it briefly. We're gonna fit and evaluate using cross-validation on all but fold K, right? So we have this outer loop, which is where I'm going through my folds, but then, so this thing is called the outer loop. So nested because there's kind of an outer and inner loop. This has some inner loop because basically, what you'll do is you're going to take maybe drawing a picture is actually okay, right? So if I have my data and I break it into a bunch of folds, right, like that, somewhere, maybe this is fold K, or I guess we're calling it, sorry, we were not calling it K, right? We were calling it V. What I'm going to do is in my inner loop, I'm going to pool and cross-validate model. I guess my outer loop should be for my hyperparameter, really shouldn't be for V, should it? Let's think about how this works, right? Nested cross-validation is nice and difficult, but let's just sit and think for a second. What are we doing here? So yeah, my outer, this is okay, right? So we're going to fit and evaluate and kind of using a cross-validation and this inner loop here. So let me just back up. So the inner loop here, what we're going to do, okay, so this is what I want to say. So we're going to fit and evaluate using cross-validation on all but fold V, and we're going to optimize over, say, our hyperparameter. All right, so we're going to kind of, basically, we're going to, do this whole procedure, right? So this whole thing here, which I was calling my new building procedure, right? We're basically going to do that in a loop, but we're going to change out, our step 2 is to evaluate. So this is going to produce a final model. So this thing is basically star, where star is this kind of procedure up here, and we're going to evaluate on fold K. And so this will give us, say, MK, and then our final metric, maybe called M, is going to be the average, for example, of the MKs. Okay. So let me back up and say this, right? So the main point is that cross-validation is just a fancier way of getting, right? So if we go back up to this procedure, right? When I say my evaluation metric here, and even my final metric, you could replace this evaluation metric or this final metric with its own cross-validated kind of thing. That's all we're doing. That's all nested cross-validation is. Right? So normal cross-validation is this deal, but you still could run into the issue where just because I've cross-validated each step doesn't mean that it doesn't mean that I don't run the same issue where if I kind of over tune on a hyperparameter, I'm going to run it. My error is going to be overly optimistic, right? So what we can do is called nested cross-validation, where you have an outer loop where you go through kind of in a similar cross-validated way, where you go through my folds, and at each point in my loop, I'm going to kind of fit and evaluate using so basically I'm going to pool together all my other folds, but fold, I guess this was fold what we call little v, right? Just to keep in mind here, right? So little v goes 1 to capital V. I'm going to pool together everything but fold little v. I'm going to fit it, and I'm actually going to do kind of a cross-validation, and I'm going to optimize over my hyperparameter. So kind of a similar thing to what I'm calling star above, where I'm, where I'm optimizing. It doesn't really even matter exactly how this optimization is done, or what parameters I'm optimizing over, or what models I'm comparing. But that's what I'm going to do, and then I'm going to evaluate that resulting model on the kth fold. That will give me some little metric, maybe m sub k, and then at the end of the day, outside of this loop, right? If that was my loop, at the end of the day, this is going to be my kind of nested cross-validated metric. So maybe I can call it my final metric is the average of the MKs, the average of each of these, in a similar kind of cross-validated way, right? The point being is that this procedure is estimating, right? So what are we doing? Either a train validation test split or a cross-validation. At the end of the day, they're just trying to estimate the generalizable error. The error if I take it from my current data set and I put it on a new data, and I apply it to a new data set. And so the procedure, this kind of inner loop here, what I'm calling the inner loop, it's estimating, this cross-validation is estimating the generalizable error if I were to use that inner procedure. The inner procedure being, whatever you want, a cross-validated, optimization over a hyperparameter, right? And the answer it's going to give us, the question to which is going to give us the answer is, if I use that procedure, what is my generalizable error? So it doesn't really even matter what step 1 here is, which is kind of where I hesitated there. It's just whatever that procedure is, this kind of net, people tend to nest a cross-validation in there. They don't even really have to. It's just, this cross-validation is gonna estimate what that procedure, be a cross-validated procedure, be some other, whatever your building procedure is. Maybe you read the tea leaves, who knows? If I do use that procedure, how is it gonna perform on new data? Notice that in this inner loop, I potentially, when if I optimize over a hyperparameter, I can actually get a different optimum hyperparameter in each of the loops. It doesn't really matter because we're not evaluating the procedure where you use the same. We're evaluating the procedure. We're not evaluating a particular model. So that's why I made a big deal of that. We're evaluating the procedure where I optimize over a hyperparameter, for example. Okay, so I think I've talked this to death, but hopefully you get a sense of what the point of evaluation is, and get a sense of that, this nested cross-validation seems a bit scary, but it's basically just a cross-validation, and people put more cross-validation in the thing they're evaluating. So it's nothing too scary there. The point being is you got to be careful with this stuff because it's easy to fool yourself. Okay, enough on that. What we want to talk about for the remainder of this lecture is bias-variance trade-off. Okay. So in layman's terms, we could define the bias of an approach as basically the error that the approach incurs because we approximate a complicated, let's say real life, that's not how you spell life phenomena with a simple model or simpler model. So my example I'd like to give is maybe, so here's here's an example. You know, maybe if I plot like grade in the course against you know, number of hours studied. Now the reality is that, you know, if I have 0 here and you know, I have 100% grade here and a 0 grade here, the reality is that the curve probably looks something like that, right? Where if I study a little bit or not at all, I'm probably going to have a really low grade. At some point, I start setting off, this is definitely going to increase my grade, but beyond some point, if I'm putting in, you know, 100 hours versus 50 hours, it's not really going to probably increase my grade very much. It'll get me from a, you know, 98 to a 99, right? So that's the model, but so maybe we could call that the truth. But what I approximate it with is, this is my simpler model. Maybe I approximate it as approximately linear, you know, apart from the ends there, you know, maybe the number hour, you know, it's approximately linear for the, you know, the middle part of the grade, where, you know, maybe not in reality, but that's the idea, is that truth is complicated, we use simple models, and we call that the error that we incur because of that bias. On the other hand, variance is basically how much the model fit changes because the training data changes. So let's think, what's my example here? My example is if I do k and n with, say, k is equal to 1, right? If I change my data slightly, it's going to give me a very different fit, right? So maybe here's my data here, and so this is my first fit, and it would, you know, k is equal to 1 is going to interpolate in that way. So this is model 1. But if I change my training data slightly, you know, if I resample, something like that, I'm going to get a pretty different model. Yeah, it goes something like that, right? I don't know, yeah, whatever the model is. That's not exactly the same, but you get the idea. So I've slightly changed my model, and I get a very different, slightly changed my training data, a very different model, as opposed to, so this is high variance, I have a very highly variant model, say k and n with k is equal to 1, as opposed to if I use, let's say, k and n with k is equal to the number of training data points, right? If, let's see if I can recapitulate these points here. If I fit, you know, that's my training data, here's my model 1, and if I slightly change my training data, something like that, you know, here's my model 2. So this would be called a low variance model as opposed to a high variance model, because my model doesn't change much. And so, as you might guess from these pictures, what happens is generally we have what's called a bias-variance tradeoff, which I think I wrote up here, bias-variance tradeoff. And the bias-variance tradeoff says that low variance models tend to go with low flexibility and higher bias, whereas high variance models tend to go with higher flexibility and lower bias. Now, it's not always exactly true, but it's approximately true. And the models above give us an example. The idea being that if I have a highly flexible model, like my K and M with K is equal to 1, if I slightly change my data, the model is going to totally rearrange itself to whatever the new data is. If I have a lower variance model, or less flexible model, if I have slightly different change in my data, I'm going to get a very different, or going to get a very similar model, even if I change my data quite a bit. So I have a lower variance model. So low variance comes from low flexibility models. Higher variance tend to be associated with higher flexibility models. The bias comes from the fact that if I have a low flexibility model, I'm effectively fitting a simpler model. It doesn't have as many degrees of freedom to play around. It's simpler. So simpler, lower bias, lower flexibility. Simpler is higher bias, but lower variance because they have a lower flexibility. A more complicated model will have a lower bias because I can fit a more complicated truth here. Maybe it's not a line, maybe it's a sigmoidal shape. And so they have a lower bias if I have more flexibility, but the more flexibility means that if I change my data, my model is more likely to change also. And so I'll have a higher variance model. So this is the bias-variance trade-off, and there's some tension. There's some tension here between these, because if you recall our picture, our training testing picture, right? What was the training testing picture? So this is maybe error, and this was, let's say, high flexibility, and this was low flex. And if I have a low flexibility model, I will tend to have a high bias. I will tend to have a higher bias. And as I increase my flexibility, my bias will tend to go down. If I have a low flexibility model, I will tend to have a lower variance, but as I increase my flexibility, my variance will tend to increase, okay? And what this means is that if I look at my MSE, my MSE is, and we'll show this, turns out that my MSE is the square of the bias plus the variance. And that is a fact we will prove. We'll do a little proof here. And so I'm going to get this kind of characteristic curve, right? Before we had seen this, right, where we had a similar picture where we had high flex, we had low flex, and we had seen that the testing looked like this, and my training looked like this, right? So we're basically looking at the testing MSE. So you could even call this test MSE, right? And the reason we get this kind of shape here is because basically if I have a high flexibility of a model, I'm going to have very high variance, and if I have a low flexibility model, I'm going to have a very high bias. And so there's some sweet spot here, right? This is the sweet spot we want to be. And there's a tension, though, right, between bias and variance. And you want to hit the sweet spot. You kind of want to play the game where you figure out where I can kind of minimize, say, my metric, my error. In this case, we're specifically thinking about MSE, but all these other metrics are basically some one-to-one function of the MSE. It doesn't really matter. As it turns out, it is exactly true that the bias squared plus the variance gives me my MSE. And so a similar kind of thing could be said about any of the other training metrics. And so when I combine these, I got to play a game where I'm trading off, and I want to kind of hit the point where these are minimized. So let's look at my claim here that MSE is the bias squared plus the variance. Okay. So basically, right, what we're doing is we're living in some world where our data is assumed, because I'm a statistician, and this is a kind of statistical learning class, to come from a probabilistic distribution. So it's assumed to be random. It's really what I'm saying here. And for sample data, we talked about MSE, which had the form of something like, it was the mean squared error. So I take my data and I take my training or whatever testing, and I'd subtract off the estimate, and I'd square it and I'd sum it up, and this is my kind of sample MSE. So this is what you might call sample MSE. And there's a similar kind of population MSE that we could talk about. And that population MSE is going to basically be the expected value of y minus y hat squared, right? And that makes sense, right? Because I guess we talked about this with kind of the squared error in kind of our what do we call it? We call it empirical loss minimization, right? Similar kind of thing, right? So this is kind of our population MSE. And if I assume my data comes from probabilistic distribution, we can, you approximate, for your training or your testing data, you're basically approximating the population MSE by calculating that sample MSE on your test data or your validation data or whatever, you want. So this is, we can focus just kind of probabilistically in the larger sense on the population MSE, and we can show that it is the bias squared plus the variance. So in terms of in terms of probabilistic statements, we define the bias of f hat, right? So remember, y hat is f hat of, let's say, x. And if we assume that our data is random, that is fed in to make f hat, this thing is also random, right? We're assuming that kind of our data is assumed to be random, and the random data is used, put in some function and create some f hat, so that f hat would be random, right? And if we view it that way, our random f hat, the bias, is defined as the average, the expected value of f hat minus the truth. So this is expected f hat less truth, or the difference between, on average, what our f hat procedure is going to give us and the true underlying function underlying our data. And we can also talk about variance, but the variance, maybe it's just like VAR, right? The variance of f hat is just going to be literally f hat is some fancy random variable. The variance of f hat is just the variance. So this is basically variability. If I have my procedure and I fit it for my data, how much do I expect that to change? Right, so we have this thing called variance and probability, right? And if our MSE, if we want to talk about our kind of MSE or population MSE, is going to be, now I'm going to drop the x's because I'm just going to call it f hat, not f hat of x, but right. So we can see our MSE is how do we want to write this? I guess if we rewrite this, right? So at the end of the day here, y is f of x and y hat is f hat of x, right? Then if my MSE is y minus y hat, I'm going to drop the x's just for expediency. You could also say that the MSE is, let's say, f minus f hat squared. I'm just going to kind of be lazy with my notation, but that's, right, that means the same thing. And I can pull this game. So this is f, and we can say subtract off expected value of f hat, add back on expected value of f hat. That changes nothing because I'm adding 0 in total. And then I subtract off f hat. That's all squared. I'm going to group these terms like this, and I'm going to push that square through. And what I'm going to get is f minus expected value of f hat squared plus expected value of f hat minus f hat squared. And then I'm going to get the cross product term between these two groups, which is plus 2 f minus expected value of f hat times what expected value of f hat minus f. And what I'm going to note is that, what do I want to note? I want to note that, did I do this right? Is that f? Yep. So let's see, this thing is not random, right? F is not random, it's just some unknown function. Expected value of f hat is whatever, a number, constant, or whatever you want to think about it, right? It's not random, right? Throw something into expectation, it's no longer random. I think I'm missing an f hat. That's why I was looking at this weird. Should be an f hat there. Cool. And so what I'm left with, if I distribute my expectation through, I get expected value of f minus e of f hat squared. Notice that this is also not random, right? For the same reason. I then get expected value of, let's just rearrange this, as f hat minus its expectation squared. And the non-random part I can pull out. In fact, I don't even need this expectation on this first one because it's not random, right? You don't need the expected value of a non-random thing. And so we get 2 times f minus its expectation, or minus the expected value of f hat, times, and I can push through my expectation. I'm going to end up with expected value of f hat minus expected value of f hat, right? If I push that through, that is 0. So actually my whole last term goes away here. This is the bias, right? It is, I guess we should rewrite this, shouldn't we? This should be in the other order. It should be f minus expected value right? Oh, I guess it doesn't matter because it's a square. Let's just not change that, does it? Undo, come back. Right, doesn't matter. It's bias squared, sorry. Doesn't matter, right? We wrote the bias the other way, and this is, by definition, the variance of f hat, right? It's f hat minus its expectation, quantity squared, you throw in expectation. So you get bias squared plus variance. So consequentially, what this really means is that what I wrote here is true, which is that we have this bias-variance trade-off, the kind of testing metric, or the expected performance of an algorithm, if we measure by MSE, but it doesn't really matter, you can measure anything else, it's all a one-to-one function MSE, generally speaking, at least for regression, that the MSE, or our evaluation metric, is bias squared plus the variance, and the variance is going to go like this, the bias is going to go like that, and so there's some sweet spot where you can trade off the bias and the variance to get a model that works well. Okay. The last thing I want to talk about real quick here is I want to talk about, let's say, sample size density. And the idea here is that I need enough data. You know what? Maybe the best way to say this is that more data tends to reduce variance. So, you know, when we show this picture, maybe I should just redraw it, but I won't. When we show this picture, right, we're kind of pretending we have some axis here of more and less flexibility, right? And I can move back and forth on this, but that's typically for a fixed data set. And if I have more data, I actually tend to reduce my variance. And what this means is that's going to shift the optimal point, and I can justify a more flexible fit. So the picture is that, let's draw a couple curves, right? So here's my bias, and nope, that's the wrong way around, right? Here's my bias, here's my variance, and here would be my MSE, which is the squared bias plus the variance, which is basically the performance of it. And so this is for one value of n. Let's say n is equal to 10. But if I move to 100, n is equal to 100, where I have 100 training points, I'm typically going to reduce the variance of my approach because I have more data to figure out what's going on, and it's going to change less because I have more data kind of constraining the fit. And so what it's going to tend to do is it's going to tend to bring this variance curve like this. Maybe my bias won't even change, but what that's going to mean is that I'm going to have a different MSE curve. And so while my optimal fit here might have been for this level of flexibility, I can often fit a more flexible approach if I have more data. So more data equals more flexible, possible, or let's say reasonable. You know, the whole game here is we're trying to navigate this bias-variance trade-off. And so you don't want to have too flexible a model because then you're going to have too much variance and it's not going to work well. But you want to have enough flexibility that you reduce your bias. The bias-variance trade-off is for a fixed amount of data. If I increase my data, I can have more data underpinning my fit, and so it will just generally reduce the variance. And so I'm going to be kind of allowed a more, or the optimal point is going to be a more flexible model. So the easy way to think about it is like let's say n is equal to 3, right? If I have 3 data points, so here are my 3 data points, what kind of model should I fit? I could fit, a super highly flexible model. And I could just interpolate these. But I don't have enough data to justify that fit. And that's going to be, it's just way overfitting to the data. It's more reasonable to fit a less flexible model, right? Because I don't have a lot of data to support some highly complicated fit. It's going to be too high variance. I'm just following the noise because I don't have enough data. My variance is going to be way too high. So fitting a less flexible fit is probably reasonable. If I go to a regime, maybe, where I have a lot of data, don't die on me now, OneNote. Come on. OneNote doesn't want to behave here. All right. Well, we're almost done. If I have a lot of data, maybe here's my data. Oh, no, this is not the time for OneNote to misbehave. All right, so here's a lot of my data points. Right, so I have all these data points, and maybe it goes down at the end here like this, right? Now I'm justified in fitting some flexible model, right? Because I have a lot of data to kind of support what a flexible model might be here. And of course I can't draw it because OneNote's gonna freak out here. Okay, let's try this again. Come on, OneNote. Well, the point is, yeah, there we go. So I can fit something that's kind of more flexible like that. You wouldn't ever be able to fit that kind of flexible model. It wouldn't be reasonable if I had 3 data points. But if I have a lot of data points, I'm kind of reducing the variance of the model, and it's more reasonable to fit this kind of flexible model. Whereas if I were to fit some simple, linear model here, that's underfitting is what we call it, because it's just not following. You have a high bias in this case, and you could actually reduce your bias without increasing your variance too much, because I have a lot of density of my data points to justify the fit. So what I really care about, or one of the things that is kind of left out when you talk about these things, is that you kind of care about the density of your data. If I have a highly dense data, a lot of data points, I can justify more flexible fits. And effectively what it's doing is it's changing the set of the bias variance trade-off that I have to play with because I have more data. Okay, we're going to stop there because we've talked enough today. But this is a really kind of important nuts and bolts. It wasn't a super technical lecture, but it's important to think about kind of evaluating approaches and what that means. And this whole bias variance trade-off. Which is super important to think about. Okay, so we'll stop there.